Hey class, today we are going to be looking at a very important topic in our studies. Please be very attentive as we move on.
Today we're going to delve into a very important topic, fluid dynamics. Fluid dynamics is central in physics and engineering. It is a fascinating field that provides our understanding of how fluids like liquids and gases move and behave. Introduction to Bernoulli's equation. What is Bernoulli's equation? Bernoulli's equation describes the relationship between the pressure, speed, and height of a fluid. It states that as the speed of a fluid increases, its pressure decreases and vice versa.
Before we proceed, please remember to subscribe to this channel, like this lecture, and comment on the presentation. Now, let's continue derivation of Bernoulli's equation.
So before we derive Bernoulli's equation, we need to make two important assumptions. One, the fluid under consideration is incompressible and it also does not offer any friction, or you can say it has zero viscosity. Well, consider a pipe that has a liquid flowing in it. And this pipe has varying elevation and cross-sectional areas through the length of the pipe. Now I want you to focus on a section of this pipe and therefore the volume of liquid contained in it. So let us say that this is that section and this is the situation of liquid at time t, so that the velocity of liquid here is v1 and the elevation, let us say, is y1. Now at time t plus delta t, or say when time delta t has elapsed or delta time t later, the situation is this. So what you can observe is that this volume of liquid, this blue part, has pushed forward, and therefore an equal volume of liquid from the other end must have also moved ahead, and it is represented by this green part. So this blue part over here has pushed forward and come over here. As a result, some liquid from this part pushed forward and came out over here, and the mass of this liquid and this liquid has to be the same. And this in fact is a continuity equation which says that if a fluid is incompressible and it is flowing through a pipe, then the volume of liquid flow per unit time in one section should equal to the volume flow per unit time in another section, or in fact the volume flow in a given time in one section should be the same as the volume flow in other section. Or in other words, if let us say the cross-sectional area over here is A1 and the velocity is V1, and the cross-sectional area here is A2 and the velocity is V2, then if you multiply the cross-sectional area with the velocity of flow, what you'll get is the volumetric flow rate, and A1 V1 should equal to A2 V2 if the liquid is flowing continuously. So the continuity equation says that product of cross-sectional area into the velocity of the fluid should be a constant. So coming back to our situation 2, that is at time t plus delta t, a part of the liquid has moved forward and equal volume has moved forward on the other side of the pipe as well. Now we'll make use of energy conservation principle to establish Bernoulli's equation. So we can say that the total mechanical energy of a fluid, that is nothing but the sum of kinetic energy and its potential energy at time t, should be the same as that at time t plus delta t. Well, not in this situation, since there are certain forces acting on the liquid and work is happening on the fluid, and subsequently we'll discuss what are the forces acting and therefore what is the work happening. And since work is happening on the fluid, the mechanical energy of the fluid is changing between two times, that is at time t and t plus delta t, and therefore the difference between two energy states is equal to the work done on the fluid. So we can write that if E2 is the energy of the fluid at time t plus delta t and E1 is the energy at time t, and mind it, E represents the mechanical energy, which is the sum of kinetic energy and potential energy, then the difference E2 minus E1 should equal to the work done on the fluid. So let us first establish each element of this equation, that is W, E2 and E1. So if E1 is the total energy, mechanical energy of this fluid, let's split this fluid into two parts. One is section A, and let's call this as section A, and this as section B, and you'll soon understand why we are splitting it into two sections. So we can say, well, the value of E1 is nothing but the mechanical energy of section A and the mechanical energy of section B, which in turn we can say that section A has a certain kinetic energy, and if the mass of the fluid here is, let's say, delta M, then we can say that its kinetic energy is half delta M into V1 square, where V1 is the velocity of the fluid over here. And then it will also have a certain potential energy, which would be nothing but its mass into G into its elevation above a certain datum level. And here we've assumed its elevation is Y1. So the total mechanical energy of section A is this, and the mechanical energy of section B is, we'll keep it as B for now. Now, using the same logic, we can say that the mechanical energy E2, which is the energy after time t plus delta t, can once again be divided into two sections. One is that of this part, which is kind of moved forward, let us call it C, and what you'll observe is that the mechanical energy of this section, that is this section, is nothing but B only. And why it is B is because every molecule, every part of the liquid over here and over here is behaving in a similar way. So if you take, let us say, a liquid molecule over here, or a chunk of liquid over here, its velocity and its elevation would be same as a corresponding molecule of chunk of liquid over here. Its elevation and velocity will be same, and it will be the same pattern across this entire section of the liquid. So we can say, therefore, the mechanical energy of both the sections is B. Therefore, at time t plus delta t, we can write the mechanical energy is equal to B, which is the mechanical energy of this part, plus the mechanical energy of this part, which is exited out, and we are terming it as C. So this should equal B plus half into delta M. Remember, continuity equation tells us that the mass of liquid coming out should be the same as the mass of liquid which is getting pushed up. And let's say the velocity here is V2. So the kinetic energy of this section is half delta M V2 square plus its potential energy is delta M into G into Y2. Now, if we were to subtract E1 from E2 or find E2 minus E1, what you'll find is that B cancels off, and what you get is W is equal to half delta mv1 square, half delta mv2 square, minus half delta mv1 square plus delta mgy2 minus delta mgy1. So now we'll go ahead and try to find what is the work done. Now you can see that there are two forces acting on this body of liquid. One is from this side, and let's say the force component here is F1, which is trying to push the liquid up, and then there is force acting from this direction. Let's call this F2, and you can see that this force component is pushing back the liquid, that is, it is not allowing it to come out. So we can say that F1 is actually doing positive work while F2 is doing negative work because it is working against the direction of the displacement. So the work done by force F1 can be written as the product of force, displacement, and let's say the displacement here is delta x1, that is, this part is delta x1, and the work done by force F2 is, we will take it as negative because it's doing negative work, is F2 into delta x2, where delta x2 is nothing but this part, and this should equate with the right hand side, which is, we've already found an expression. And if we once again expand the left hand side further, we can say that force 1 is a product of pressure into the area of cross section over here, and if the area of cross section here, let us say, is A1, then we can write this as equal to pressure over here, and let's say the pressure over here is P1 into A1 into delta x1. Likewise, we can write the same for this part. If the area of cross section here is, let us say, A2, then we can write force 2 is nothing but the pressure over here, and let's say the pressure here is P2 into A2 into delta x2, and this should equal to the right hand side, which is this. Now once again you'll realize that the product of cross-sectional area into the distance covered, that is this part, is nothing but the volumetric flow rate. So these both are volumetric flow rates, and therefore we can write that this is nothing but delta V, or the volume which is flown. And from continuity principle or continuity equation, we know that this expression, that is, if we call it delta V1, and if this is delta V2, both should be equal. So we'll write it as volume V, or delta V rather. So we can write this as P1 should equal to the right hand side. And if we divide both sides by delta V, what you'll get is, on the left hand side you'll get P1 minus P2, and on the right hand side, when you divide delta M by delta V, what you get is density of the fluid. So we can go ahead and write this as half rho, where rho is the density of the fluid, and it is nothing but delta M upon delta V into V2 square, which, mind it, here is the velocity, not the volume, minus half rho V1 square, which is the velocity at point 1, plus rho gy2 minus rho gy1, because in each of these expressions, when you divide delta M by delta V, which is the volume flown, you get the density of the fluid. And if you rearrange this equation, bring all the 1 subscripts on the left hand side and 2 on the right hand side, what you get is this. And this is what you call the Bernoulli's equation, which essentially says that if you sum up the kinetic energy, the potential energy, and the pressure at any point, it is a constant. So let us try to interpret this equation in various ways. Well, the first one could be that of liquid, which was static or stationary, that is, velocity V1 and V2 are 0. In that case, the equation would become this. And if you rework this equation, what you'll get is P1 minus P2 is equal to rho g into Y2 minus Y1. And this starts looking familiar, because rho g Y2 minus Y1 is nothing but rho gh. And this is what we learned in the earlier lesson, that when a liquid is stationary, the pressure between 2 points is equal to the product of the density g and the distance that separates those 2 points. In this case, it is Y2 minus Y1, and we've taken that as h. So it kind of, this Bernoulli's equation kind of validates a situation where the liquid is stationary. Well, the second could be that if the elevation of the fluid is constant, that is, this part is at the same level as this part, the equation would look something like this, which essentially means that if velocity of the liquid increases at a point, the pressure must drop to keep this equality intact, or the sum of pressure and its kinetic energy per unit volume should be the same at all points if the elevation is same. And the link between the change in speed and the change in pressure makes a lot of sense if you consider a fluid element that travels through a tube of various widths. When the element nears a narrow region, the higher pressure behind it accelerates it, so that it then has a greater speed in the narrower region. And when it nears a wide region, the higher pressure ahead of it decelerates it, so that it then has a lesser speed in the wider region.
Alright, it is hoped that you enjoyed the lecture. Don't forget to subscribe, like, and comment.